In this video, we'll be introducing the concept of isolines and and how electric field lines are associated with them, and we look at some simple situations. So first things first, let's see what isolines really are. So far, we know a bunch of little ideas. We know that if we have a point charge, say a positive charge, the electric field lines around a positive charge seem to be going out of the positive charge. So we know that this is conventional. We've chosen the lines to be moving away from the positive charge in this case, for positive charges, and for negative charges, we have the lines going into the charges. Now, we've also introduced the idea of the potential. And what we know is for a positive charge, the potential is given by kq over r, or rather for a point charge, the potential is given by this. So we know potential, which happens to be a scalar quantity, okay, and in the case of a point charge, we know that at the same distance from the charge, no matter where you are, okay, if you are at a particular distance from the charge, the potential is going to be constant. So in the case of a positive point charge, if you were to be on the surface of a sphere with the charge at the center of the sphere, okay, then the potential on all the points on that sphere would be constant. We would call that an equipotential surface. Okay, now on a two-dimensional surface, if you were to take the sphere and it would intersect the surface in a circle. So in a two-dimensional surface, we represent these equipotential points, okay, by some lines, and in the intersection of the sphere with the plane gives us a circle, which happens to be called the isoline. Okay, so an isoline essentially is some curve where the potential is constant. So throughout the curve, the potential is constant. Now there are a few things that could be useful. So if you were to take any other charge, let's take a negative charge. Okay, if you were to move this negative charge from one point on this isoline to another point on the isoline, the work done on the charge would be zero. Okay, and the reason being that work is equal to negative q delta v, and for an isoline delta v is zero, and therefore the work done would be zero. Okay, now at any other distance we would have another isoline. So let me just draw this as a separate picture. So if you have a plus charge, okay, we could draw isolines around it. So one isoline would be, say, a circle around this point charge, okay, at some distance r. At another distance we could draw a second isoline, and so on and so forth. So each of these circles would be isolines. We can say that the potentials are v1, v2, v3, and we can do the same stuff that we've done in the case of a point traveling from one potential to another potential. We can find the work done, we can find potential energy changes, all using all the ideas that we already know. Now, there is an important relation between isolines and electric fields. What we know is that the electric fields are always perpendicular to the isolines. Okay, so in the case of a positive charge, we could draw the electric field lines pointing outward, and these lines would be perpendicular to the isoline at all points. So wherever they intersect an isoline, the electric field will always be perpendicular to the isoline. Now, we knew from past practices that the electric field lines, okay, will come out of a positive. They seem to be pointing away from a positive charge. Now, we also knew that the field points in the direction of decreasing potential, which makes sense in this case because V1 would be greater than V2 would be greater than V3 as we're dealing with a positive charge, since V1 is KQ over R1 and V2 would be KQ over R2, and since as R increases, the potential would decrease. So all this is consistent with the stuff that we know. Okay, so let's make a note of this. The electric field lines, okay, are perpendicular to the isolines. Okay, and we already know that E, okay, will point in the direction of decreasing potential. Okay, so we understand these ideas as well. So what we need to know here is, first of all, what are isolines? Isolines are lines where the potential is constant. It does not change. In the case of a positive charge, the isolines would be circles around the positive charge, with the charge being at the center. Electric field lines are perpendicular to the isolines, and they will point in the direction of decreasing potential. Okay, so using all these ideas, we can do a bunch of little things. Okay, so let's say that some charge distribution creates, okay, isolines of this sort. All right, so let's say that this is equal to V. Here the V is equal to 0. Here V is equal to, say, 10 volts. Here V is equal to, oops, 20 volts. V is equal to 30 volts. Here V is equal to minus 10 volts. Here V is equal to minus 20 volts, and so on. Okay, now if we were to take some random points, what I would like you to do is, at each of these points, draw an arrow that represents the electric field at that point. Okay, so let's see what the electric field would end up being. Now pause. All right, so let's assume that you have some arrows. Okay, we'll figure out whether they're correct or not. So let's understand. We know that the electric field is always perpendicular to the isoline. So at each of these points, the electric field lines would have to be perpendicular to the isolines at these points. So I could draw it like this way. Doesn't have to be perfect, but just try to make it, close to being perpendicular. And if you are unsure, not able to draw that, just make a little sign that represents that, hey, these things are perpendicular. Okay, now we also need to figure out the direction. And if you see what we said earlier, E points in the direction of decreasing, oops, points in the direction of decreasing potential. So in this case, the potential is decreasing from right to left. So our electric field lines are going to point in this direction. Okay, so now we can also ask some other questions. Hey, what happens if we release uh, say an electron, okay, at this point? So let's say I have an electron here, E, okay, that we release, and the charge on the electron we know is minus 1.6 times 10 to the minus 19 coulombs. So if we were to release this electron, which potential would it travel towards? Would it go to the left? Would it go to, kind of to the right? And we know that an electron has a negative charge, and it travels from a low voltage to a high voltage, okay, and therefore the electron would travel in this direction. Okay, and each time it crosses, the 10 volts, like in this picture, what we can do is we can calculate the energy that it gains. So let's say if the electron travels from potential A to potential B, in this case, okay, isoline A to isoline B, then the energy that the electron would, the potential energy change of the electron, which is simply Q delta V, would be equal to negative 1.6 times 10 to the minus 19 multiplied by the 10 volt difference in this case. Okay, and we expect this to be negative because in nature, whenever things do what they want to do, the potential energy will decrease. Okay, and then correspondingly we can find the work done by the electric field, which is the change in the potential energy, which happens to be equal to 1.6 times 10 to the minus 18 joules. Okay, so when you multiply this guy, you get 10 to the minus 18 joules, and we have an answer there. Okay, so a lot of these basic things could be done with these equipotential lines, and I hope that you've understood what's going on in this case. Okay, so that is it for this video.